Okay, we are having some problems with the sound. We don't hear you.
How about now?
Now, yes, it's okay.
Oh,
Thank you.
okay, good. Thank you, Sophia. And thanks to everyone for giving us the opportunity to talk about Moltex, which I shall try to do for no more than the next 15 minutes. If you could move on to the next slide, please. So our partner company, EDOM, are going to talk next, and they will, Oscar from EDOM will describe the technology. So I'm not going to talk about the technology particularly, but more about the commercial aspects of the market and of reactor design and of our reactor design. We're a UK company. We operate primarily in Canada right now for reasons that will become apparent. And we have a variant of a molten salt reactor design. Some crucial differences between our design and a generic molten salt reactor, which Oscar will describe much better than I'm able to. The key features of the reactor, though, are firstly that it's low cost. So we would expect a price per megawatt hour of less than 40 euros. I'm going to talk about using recycled nuclear waste as fuel. I'm going to talk about energy storage, but not much, because TerraPower have covered that subject very thoroughly, I think, and a little bit about hydrogen. So if we could move on to the next slide. However exciting the technology is, the issue for climate change is the cost of power generation. This is a study done in the US by the Electric Power Research Institute that shows what impact nuclear can have on the on electricity generation at different price points. And the price points here are the overnight capital cost of constructing the reactor. So at $3,000 a kilowatt, nuclear could grow its contribution worldwide. At $2,000 per kilowatt, you start to see really meaningful displacement of coal and gas. And that's really driven by the cost of gas. And so we have always taken the view that this is an economic business. We're only going to get rid of fossil fuels if we can provide a cheaper alternative. If you can move on to the next slide. The challenge for current nuclear power, current generations of nuclear power, is that they are not cheaper. When first built, actually, nuclear power was cheap, but the experiences of 3 Mile Island and of Chernobyl, and perhaps more recently of Fukushima, have all acted to drive up the safety requirements, the containment systems, the backup and so forth, that has led to nuclear power becoming really very expensive. The bar on the right is Hinkley Point C, a 3.2 gigawatt pressurized water reactor being built in the UK at a cost of £22 billion for a 3.2 gigawatt reactor. That's very nearly $9,000 per kilowatt. So something like 4 or 5 times more expensive than it would need to be cost competitive with fossil fuels. So that's effectively the issue that we're trying to deal with here. If you could move on to the next slide for me. I'm not going to talk about how the reactor works. Oscar will do that a little bit, but in a similar way to the previous speaker, this is a reactor which has no contained pressure. And no contained pressure means no pressure to release. There are also no radioactive gases produced by the reaction. And those two things are the real hazards in current nuclear power. The fact that a release of pressure, an explosion, if you like, also threatens a release of radioactive gas. And it is the containment of those things that adds cost to nuclear reactors. Because that's not possible, our reactor ends up being about a 20th of the size of a current pressurized water reactor. And that, as you might expect, has a fairly significant impact on its cost. And so again, if you could move on for me, please. We would expect a 500 megawatt reactor to have a capital cost of about 900 million euros. and at peaking, a peaking reactor, and I'll describe exactly how it does that later, at about 1.35 billion euros for a 1500 megawatt reactor. And both of those costs are comfortably below the target we've effectively set ourselves of capital costs of under $2,000 per kilowatt. So we will talk a little bit more about that, or Oscar will talk a little bit more about that in a moment. But look, that deals with one objection to nuclear, right? One of the objections to nuclear power right now is that it is very expensive. The other objection is that it produces hazardous waste. So if we could move on again. I'm going to use Canada as an example. Right? The Canadian plan at the moment is to build a deep geological repository. And like many countries who are pursuing that solution, they are going through a painful process of trying to find a site and trying to find people who will agree to have a deep geological repository in their territory. The budget for that is $22 billion. That's about 15 billion euros. And interestingly, only 20% of that cost is a fixed cost of construction. About 80% is a variable cost, which relates to the volume of waste stored. And mostly that is related to the fact it takes quite a long time to get the waste into the DGR and stored. And so the more waste you put in it, the longer it has to be open for before you can close it, seal it, and leave it for the next 300,000 years. In Canada, there will be, by the end of life of their current fleet, about 110,000 tons of spent fuel. If we could move on to the next slide. So we've got an alternative for the use of that fuel. That 110,000 tons of spent fuel contains just over 400 tons of plutonium, which is sufficient to power our reactors for 60 years, a total of 5.8 gigawatts of reactors. And the process that we use for recycling that fuel, again, Oscar will talk about this in a bit more detail, reduces the volume of high-level waste by 99% and reduces the radioactive lifetime of that waste from 300,000 years down to just 300. The reasons for that are primarily that our reactor can tolerate not just plutonium, which it burns, but also higher actinides. And so the recycling process that we use does not need to produce pure plutonium. It is not traditional reprocessing in the way that happens in France right now and used to happen in the UK. It's therefore a much simpler and cheaper process, and the waste streams that are left over from it contain none of the higher actinides and therefore are very much easier to deal with. And we expect there to be an economic benefit of this process, even if we never build a reactor and never use the fuel. And so just recycling the waste into different forms makes the storage very much simpler and cheaper. And we estimate we could save Canada about 50% of the total costs of its deep geological repository, which is $7 billion, right? So euros, not an insignificant amount of money. I thought it'd be interesting just to compare that to Spain, actually, briefly. So if you can move on to the next slide for me. I mean, there are 7 gigawatts of reactors in Spain right now, pressurized water reactors, well, light water reactors, with no current long-term disposal plan for the waste. The last of those reactors, as I understand it, is expected to close in about 15 years' time. So the waste accumulated by those reactors over their lifetimes would be sufficient to power a fleet of 6 of our 500 megawatt reactors. So 3 gigawatts of reactors for 60 years, fueled by a single recycling plant, a Watts plant, and massively reducing the liability and the challenge of dealing with the waste that has been produced up to now. So we think there are some interesting potential in any country, indeed, that has existing spent fuel and is engaged in the process of trying to decide what to do with it. Okay, could we move on a slide, please? So, just like TerraPower, we too have a molten salt-based thermal storage capability. I won't go through it in detail because it is exactly what has already been described to you. It's a technology that's in use in the concentrated solar industry. The reactor produces heat at the right sort of temperature to make this a particularly efficient process. And it's a necessary capability for nuclear power going forward. Because if we accept that wind and solar power will be significant parts of the energy mix going forward with their 40% capacity factors, we clearly need a solution for the other 60% of the time. And the only solution that exists right now is gas. And so it's competing with gas in the peaking market that we think is crucial for the new generation of nuclear reactors. We've also looked at the pricing impact, by the way, and using the UK market, which is where the price of electricity does vary by the half-hour period. If you generate baseload electricity, the wholesale price in the UK was £40 a megawatt hour in 2019. If you just generate electricity for the highest 24 hours in 3 days, that price more than doubles. And so there's a very significant additional amount of money that could be made by an operator operating in a peaking market. And we think that will be of great interest indeed. Okay, if we can move on. The hydrogen economy is an extremely big subject, and in the couple of minutes that remain, I don't think I can really do it justice, except to say perhaps that solving the problem of clean electricity generation is about a third of the task that faces us with regard to climate change. The other 2/3 is really heating, transport, and industrial processes. And it seems very likely that hydrogen will form a crucial part of the solutions to that aspects of climate change. We actually have a second reactor shown here as the SSIU, a thermal spectrum reactor, which produces much higher temperatures and has a role in industrial process heat and also in high temperature electrolysis that could help generate hydrogen at a sufficiently low cost to address these market segments. But we just can't really talk about that now. I think it's just going to take too long, I'm afraid. So let's move on and talk about where we're up to now. As I said, we're operating in Canada. We're making most progress in Canada. The reason for that is that the Canadian government is particularly well joined up and has a clear strategy for nuclear. And that's federal and provincial government and the nuclear operators, New Brunswick Power and OPG and Bruce, are all on exactly the same page, and they have a 3-stream strategy in Canada, which is being executed now. And some of the announcements you have seen or will see will fit exactly with the strategy. And so, in what they call Stream 1, the intention is to deploy a reactor at the Darlington site in Ontario. OPG are leading this activity. And at the moment, they have a short list of 3, X-Energy, GE Hitachi, and Terrestrial. Their objective is to deploy towards the end of the 2020s, 2027 or 2028. And they are most focused on a deployable technology. Stream 2 is advanced modular reactors. That's being led by New Brunswick Power, who have selected 2 reactors to build. One of them is ours, and one of them is ARC Canada. And so 2 reactors will get built, including ours, at the Point Lepreau site in New Brunswick for 2030 deployment. And then Stream 3, which is micro reactors, so small scale reactors, which are important in Canada. Actually, they have a lot of isolated communities and industrial sites where small-scale nuclear could well work very well. And USNC, Ultra Safe Nuclear Corp, has an agreement to build a demonstration microreactor at Chalk River, which is the Canadian Nuclear Labs site. So that's why we're in Canada, and that's why we're doing well in Canada, because essentially government policy has made that possible. And I think the Canadians are a year or 3 or 4 ahead of most other countries in that regard. Okay, and I guess the final slide then is what we would call the so what question. Right? And I think I'd remind you of 4 things. One is that cost really, really matters. Being cheaper than fossil fuels is absolutely vital if we're to make any progress in climate change. I think recycling of waste matters primarily for reasons of public perception. So the social license of nuclear is massively improved by having a clear and obvious and green solution to the question of nuclear waste. Peaking power matters, because actually you can't implement renewables unless you have a complementary source that operates the other 60 or 65% of the time. And finally, we would say that hydrogen matters, because electricity generation is only about 1/3 of the problem. And the other parts of our fight against climate change need solutions too. So that was all I was going to say. I hope I haven't overstayed my welcome, and thank you very much for your attention.
Many thanks, Simon, for your presentation.